So you guys hear me okay? Yeah? I think everyone is in the back of the room. No, we should switch this. We should cut up front, right? Or faculty in the back. Anyway, so yeah, I will talk a little bit about opportunities of artificial intelligence for Earth applications. I call it kind of loosely. Of course, AI is sort of in the news, right? And everyone talks about AI. I think it's probably for some of you a controversial topic. I like this chart quite a bit because it tells the story, the history of artificial intelligence. So it's not all that new. Although some people think it's new. We had brittle AI systems already in the 80s and before expert systems. Then we have machine learning. There's basically regression models or decision trees, so something relatively simple. Then we created larger and larger data sets. We had better and better computers that made neural networks viable, and then even deeper neural networks. Deeper neural networks means many, many different layers. So the time of deep learning came. Right, neural networks allow you to model more complex things. And now we have what people call sort of the era of foundation models. Now, when you read the news and so on and so forth, you're going to see, well, a lot of people talk about Gen AI. Now, I don't like the term Gen AI at all because what that really means is predictive AI. We've been doing this actually for a very, very long time, so there's nothing new. But in general, when people talk about Gen AI or agentic AI, it's really foundation model based. Now, foundation models are different from what we had before because everything we did before was relatively narrow, task focused. So that models could do one task, could do some categorization, some segmentation. But now we have sort of models which have learned some basics. And then these models can be fine-tuned to multiple tasks. And I think if you think about this from a science perspective, that's actually very interesting because, look, in science, we're all about foundations and learning some foundational behaviors. So that's why foundation models offer a unique opportunity potentially for science. I'd like to explain a little bit how foundation models work, because many people, I don't think really understand exactly what they don't do, and maybe some skepticism also comes from that. But what you really do in these very advanced models, for example, ChatGPT, you take some data, a very large data set. Let's say you take Wikipedia. And then what you do is you mask part of this data. So you redact it. You take some information away. That's the idea of self-supervision. And then you have this thing in the middle, which is the model. And then you ask that model to learn what you've masked. And that model is actually able to track the context of all the information. So what this model will learn is it will learn how to predict these missing blanks. It will learn that the word cream cheese is close to the word bagel, and that the word coffee is close to the word morning, etc. So what you do in this step is you basically teach a model to predict the missing token. People talk about tokens because all these breakthroughs in AI actually came from natural language processing, and there you have the notion of tokens, which are words, right? You have quanta of data, so you need sort of a quanta type of concept. So once you pre-train it, it's similar to education, right? You're in K-12, you go to college, and then you get fine-tuned. So now this model already knows language, has learned something. It knows how to fill in missing blanks. But now you want this model to become an expert in atmospheric sciences or in electrical engineering or whatever. And so you fine-tune it. So you can fine-tune these models. And there's a huge advantage because or you can fine-tune with much less data. That's also interesting, right, for a lot of science applications, because in science we often lack a lot of data, right? We're in a different regime. So in that sense, we can basically take advantage of the foundation, and we can train with significant less data. And then finally, what you do is you run the inference. So 3 steps. Now, when you train, this one is usually computationally very expensive. This is relatively cheap computationally. And then inference is the cheapest. So that's what you do when you ask ChatGPT a question. That's basically just the inference of the model. So I did work, and I am working quite a bit on what I call geospatial foundation models. So foundation models for weather. Foundation models which are pre-trained, not on text, but on weather information or remote sensing, etc. And so how do you do that? Well, you do this exactly what I just showed you. You take the data, let's say it's weather reanalysis. That's very convenient to use. You have multiple channels, parameters, variables. You can think about it in this gridded form if you want. You mask, and then you teach the model to predict what you've masked. And the model will learn to predict the missing patches based on the information it has, based on the context. So something relatively simple. So you wonder whether this is useful. Why would you do that, right? Of course, it is useful because maybe you can use it for assimilations. Maybe you can use it for movement of clouds. But you can also, of course, mask in time. So you can use it for forecasting. And you can also use that model to learn the differences between the relations between all the different channels. So that's what you do. Now, there's lots of details to it. But when we did that a while back, it's not just me, but quite a large community of folks, of course, working on AI weather models, we got basically 2 results. 2 important results, I would say. The first one is that is actually not quite surprising, but this AI model is many, many orders of magnitudes more efficient than compared to the WRF model, an NWP model. So much more efficient, much faster. Something like, it depends on how you do the comparison, etc. But you're talking about many, many orders of magnitudes, 5 to 6 orders of magnitudes faster. So that's interesting because you can potentially run very large ensembles, or you can run these things at very high spatial resolution. So that's great. So these are just different models, and they all show basically the same type of acceleration. The next thing is these models aren't quite as inaccurate as people thought. In fact, today, I know this accuracy question, of course, is an open question, so I really don't want to go into that. But they are quite performant, even in conditions which are considered to be extreme. So this is an example we did with a model I worked on for Hurricane Ida. Brian knows everything about that one, right? And you get pretty decent results. So you get accurate results, they're fast. So that's quite amazing. In fact, it is so that ECMWF, right, which is the European Weather Agency, they're now running AI models in parallel. And when we started that maybe 5 years ago, I mean, that was completely out of the question. So a huge shift. And so it's really interesting that we got this result. Now, these models, just to say, you can forecast, can fine-tune, can do all kinds of things with them. Because remember, whether this is a foundation model for weather or trained it on satellite data, it has learned the spatial, the temporal, and the channel features which are relevant. And so I had a lot of fun with many different projects in the last 2 years. This has nothing to do with atmospheric sciences, but this was actually featured in the New York Times, where we actually used foundation models pre-trained to do feature recognition of geoglyphs. I don't think you can see this here, but this is actually a geoglyph. 2,000 years ago, they were carved into the Peruvian desert, and we discovered with our AI method in 1 year over 300 of those geoglyphs. This is actually a whale with a sword, and that doubled in just 1 year the numbers of known geoglyphs. So AI can be actually used. So we did other things. We don't have time to get into that. So that's all great. So what are we doing now? I mean, as always, when you make a lot of progress in the field, like these AI weather models, for example, there is a lot of technical debt, to be honest. So there are still many, many open questions. And so these are all really good questions to think about. The one question is, today, if you look actually under the hood of these AI weather models, but the idea is they learn everything from this data set. But the reality is they don't. And you can prove this relatively easy. So today, they're learning a very small part of the data, and they become predictive with respect to that. But they're really not taking advantage of the complexity of these very large geospatial data sets, which you can imagine can be really, really complex because you can have weather layers. So I like to think about this as a 5-dimensional, 6-dimensional tensor. The other interesting ideas working with Kamazima and Christopher on, can we repeat this actually for oceans? And so we already have sort of a prototype of an ocean foundation model, but it's really a sort of a very early prototype. The other interesting question, which I find is probably the most important one. So think about it. So we have now AI models that forecast weather quite well. We know that empirically, but we really don't know why. We don't. So the idea here is that we actually think about how can we learn what this AI model has learned so we can translate it into something we can understand. And so there's a lot of interesting questions you can think about it, but this is really something where you go AI from something which is task optimized, right? Where you only care it works, and then that's fine. But we're really asking the question, what has this model learned? And how can I figure out what it has learned so I can potentially create some new knowledge? There are other ideas so there are other projects, for example, with Papdos, using these foundation model approaches for adaptive sampling. And then, of course, I'm also super interested in electric grid applications. I think I stop here. Hopefully you have any questions. Hopefully you have a lot of questions. Great. Question.
Hendrik, what's the speed bump to these models learning more complex data sets?
Yeah, so it is. Here's a simple back on the envelope calculations if you would have more time. But think about it. This is just an example. You can think about this data, right? There's latitude, longitude, time, it has different channels.
Yeah.
You can have different modalities. You calculate the numbers of tokens, and tokens is a strange concept in this, but you can come up with a token structure. The reason, again, why we're using tokens is because all the architectures come actually from the text domain. But you do that, and then you think about to keep track of the relations between this modality at this timestamp and this modality on that band, let's say on a different location, on a different timestamp.
It's just
It takes you 10 to the 30 bytes, which is 15 orders of magnitudes larger than the largest AI computer we have today. So that's a problem.
it's just size, sheer size.
Yeah, but of course, you can sparsify the matrix. And so then the question comes, how would you do this in the most intelligent way? What does make sense? And a lot of domain knowledge actually comes into play right there.
So there are so many opportunities and examples where you can imagine AI doing a great job with something that is very difficult to simulate in an explicit process way. For me, the best example is atmospheric aerosols, where for the organic part, the aerosol mass is the end result of hundreds of different chemical processes, and people are totally vexed about, oh my God, do we have to write all those down in the kinetics and all that stuff? But the data that we have on observations of aerosol abundance, along with emission models and emission observations for the precursors, along with the reanalysis of the meteorological conditions. You can imagine that an AI model would be great at predicting, but the real value comes from then saying what you just said. What did the model learn that we don't know, and what do we do with that information? Are there other examples like that where people are working on? I mean, aerosols kill, I don't know what it is, a few million people a year. So there should be a lot of funding for that, and it seems like we ought to be in aerosols. It's an area where there's lots of overlap with BNL and local agencies around New York City. We ought to do that.
Yeah, so that's aerosol is definitely sort of a really interesting candidate. Of course, with Brian, we look at severe weather, right? Understanding extreme precipitation, super complex. And then, as said it perfectly, it's great that we have a model which performs well, and that we have confidence it can perform well. So now we come to the next step. What has it learned? Does it memorize? That would be very disappointing. Or does it really? Can we really use it to discover the knowledge? But again, this notion that these models are just memorized is actually already disproven because people do out of sample tests, and models perform quite well still. Right? Anyway, that is the opportunity.
Fantastic, crazy area of science where you want to reverse engineer your own model. It's exciting.
I think my question was related to John's, but we could talk afterward, but it looked like there were a couple of questions on the chat that might have come up.
Oh, maybe yeah, I've been running the chat.
Thanks.
Okay, Minghua, do people use multiple scale special tokens so that coarse resolution data are first used, then high resolution pixel level data to train foundation models, training workload?
Yeah, so he's talking about a hierarchy of attention. Okay. And people are using or looking into that. Again, the question is how you do this the best way, right? And what makes physical sense. And but yeah, people are looking actually. Yeah. Very good question.
So we'll wrap that. And I'm going to switch one question while I'm switching presentations.
Yeah. Is AI simply correlative, or does it understand physics like the Navier-Stokes equation that's going to constrain things more than just the simple observations that you're throwing into it?
So I think that is very much, these are very much research questions. How much has it really learned? Think about the AI model, it is a different way of solving the equations for weather events, right? If you train it on ERA 5 is being simulated with simulation tools. Now I train an AI model to do that. The AI model is a better solver for that particular case. Know that works. So then the next question is, how can you ensure that the model has actually learned physics, or does it just memorize? The way you can figure this out is by giving the model new scenarios, let's say, right? And then test whether the results are physically consistent. That's one way to think about it, right? Does it actually obey the physics?
And actually linking it to the physical
Or
equations,
linking it-
like the
exactly,
thermodynamic
linking it to
energy
physics.
equation, basic mass continuity. So you can train the model in concert with those equations and therefore the model should learn those terms and equations, latent heat, all the things.
Exactly.
And so then when you have a scenario, the model can, after that training, can hopefully partition those terms based on the physics. That's the hope. That's what
That's a
what
research.
we're hoping to do.
That is a research.
We'll see.
Ask us another year.
Anyhow, thank you, Hendrik.